some applications of electric potential, but then I want to also tie it into how that relates to different kinds of circuits. And so we'll be looking at that today in lecture, and then also I have a group quiz that is a little more closely aligned with the kind of stuff that you might see on the quiz on Tuesday. And so that is what we'll finish up with today, is working on that group quiz. Also, your exercise that I gave you when I was gone, I have the solutions here, which I'm happy to go over in more detail with you if you want, in preparation for that quiz. Now, a reminder that that quiz will not include the subjects from electric circuits. And so that will just be the chapter 23 on Gauss's law and 24 on electric potential. But I'm going to be looking at some stuff that kind of overlaps between the two in the first couple of subjects today. And also, I want to do kind of a fun topic, because we've been working pretty hard. So let's do a special topic today on lightning. And so that is another thing that I want to do, is look at how lightning works, and then look at some examples of how we could actually calculate the amount of potential damage that a lightning bolt could inflict on you if you were struck by lightning. Okay, and so let's start then with, first of all, we before looked at Ohm's law, and we wrote that as delta V equals IR. That is actually a more specific case of this more general relationship. And so I want to explore that to begin with here. This is the most general starting point for current. And so we know that inside of a wire, you've got some local electric field, and that's causing charges to move. And that result, then, of an electric field inside of a conductor causing charges to move is what we call a current. Okay? And so we can think in terms of the applied electric field, this is the cause, as equaling, and this is what we call the resistivity of the substance, times J, which is the current density. So this is a more general description of V equals IR, but it talks more in terms of the electric field that causes the current to flow. And we define current density J as equaling current per unit area. And so by calling that a current density then, essentially what we're saying then is how much of a flow do we have over a particular area. And so it's kind of like traffic density. You know, you could have a much greater amount of traffic density if you have the traffic moving through a smaller area. And so here, if the current is moving through a smaller area, then you have more of a density of the current over whatever area it is that you're talking about. And so with that definition then, we can say, and here this is, in a more general sense, going to be written as di dA. But this is true if and only if the current I changes over the area. In other words, you might have more current in the center and less current out near the outside. Or the reverse. You could have less current inside and more density out near the surface, like this. And this actually tends to be a little more true because electrons will tend to repel each other. So as the electrons repel each other, they can get a little farther apart from each other, and so then the current is going to be more concentrated near the outside of an area than toward the inside. But there are a lot of other applications, and we'll look at some of them today. But here, this is true if the current is constant over the area. In other words, a uniform current. And so why is this considered a more basic relationship? Well, because before, recall that we described the current, and this was a very important result from the lab lecture. So remember that that's all being included in here. This was equal to the number of charge carriers per unit volume times the charge on an electron times the drift velocity times the area. Okay, so that was our description before for the current. This is the number of carriers per unit volume times the charge on each charge carrier times the average velocity of the electrons through the wire times the cross-sectional area of the wire. Cross-sectional area A. And so we have a current flow this way, which means that the electrons would actually be going the other way with an average velocity that would be v drift. The charge on the electron is negative, v drift is negative. So it's as if we had positive charge carriers moving to the right. So we can see then that our current density then is just given in terms of the number of charge carriers times the charge. So this is the amount of charge per unit volume that's moving times the average speed of the charge. So there's no dependence on the geometry of the wire. And so that's what makes the current density kind of a more general description for what's happening, is we can talk about a local electric field that's produced within the wire. We can consider that to be, in this case, constant. But in other cases, if the area were to change over time, then the electric field would decrease if the area got bigger. But this resistivity has a temperature dependence and is a constant for the substance. So if the resistivity is large, that means that it will act more like an insulator. But if the resistivity is small, then it would act more like a conductor. So small resistivity would give rise to a large current density. The current density in this case would be directly proportional then to the average speed of the molecules that are, or the, not the molecules, but the electrons that are moving through the wire. Okay, so with those ideas in mind then, we can then derive Gauss or Ohm's law from the idea that we have a constant electric field over a distance. That's delta V. But if the electric field is equal to the resistivity times the current density, then we can write the current density as NQ times V drift. Okay, and so you could rewrite that then as delta V equals current density times resistivity times L. Okay, but the current density we can write as I over A. Right? You know the current density for, at least if we're dealing with this case, where we have a uniform current over a constant area, then the current density is I over A times L, so that gives us this constant times I. Okay? And that constant is what we call the resistance of the long straight wire. And so this is Ohm's law then, where we call this the resistance, this is I, and then this is the resistance to current flow. So this is a particular example for R, for a long straight wire. Our resistivity times the length of the wire divided by the cross-sectional area of the wire. And so here's our wire. It has some length L. And let's say it has a radius R, so that the area would equal pi r squared. This gives us the expression for the resistance of a long straight wire. So where would this come in handy? Well, you might have a power tool, but you've got to work on some fence that's really far out near the edge of your property. And so you've got to hook together a couple of 100-foot long extension cords. Then the length of the extension cord, then, if it doubles, that's going to double the resistance through that part of the circuit, and that's going to be an extra resistance above and beyond the resistance of whatever your power tool is exerting. And another example of this would be when we're doing our little circuit labs, and we've got say a couple of resistors either in series or parallel, we're neglecting the resistance of the connecting wires. But if the resistance is only on the order of 1 ohm or so, that might not be a good assumption, because we could easily have a 1 ohm resistance just in the resistivity of that, say, copper wire times the length of the wire divided by the cross-sectional area. So this is useful, and it's also important in understanding other phenomena too. Like, for example, in a lightning strike, you have lightning hitting the ground. You might have 10,000 amperes of current striking the ground, and then the electrons are going to move out in a spherically symmetric fashion from the point of impact. And so you could think of the ground then as being a spherical resistor. And so to figure out then the current flow through the ground, you would need to know the resistivity of the ground. But in that situation, you have a constantly changing area. So that is something we'll get to a little later on today. But for the moment, let's just think of it in terms of a long straight wire. So if we have a long straight wire like this, let's ask the following question. Let's say that we keep the resistivity constant, but we double the length and the radius. What effect does this have on the total current? Let's say the total resistance of this wire. Let's just look at the resistance, not the current. So we double the length and we double the radius. Think about that for a second and then check with your neighbor. See if your neighbor agrees with you, what that would do to the total resistance. If we double the area, what does that do to the resistance? And no, if we double the area, what would that do to this resistance? It would be half, right? So a lot of times we think of a big wire as having more resistance, so it's bigger around. But no, the bigger around, the less the resistance, right? Because it's like having a 4-lane highway versus a 2-lane highway. you have a 4-lane highway, it says, and I've seen this a lot on the freeway lately, lanes merge, traffic slows down, right? Be careful. And then there's a highway patrol car there to make sure that you don't slam into all the traffic that is in front of you. And so that's because there's more resistance because there's more constriction. Okay? And so if the wire is thinner, that means that the resistance has gone up, not down. So you take a little lampshade wire, and you've got more resistance than in some big, super high gauge wire that it would have the same length. Okay, so that's something to keep in mind here. So we may have just this idea in our mind that wires that are bigger around have more resistance, but that's not the case. If everything else is constant, the bigger around the wire, the lower the resistance. That's like opening up to 4-lane traffic from 2-lane traffic. You've got less resistance to traffic flow, and you don't have a traffic jam anymore. Okay, so what about this one? What about this problem? Doubling the length does what to the radius? Does what to the resistance? Doubles it. Okay, so R1 then would be rho times 2L over, and then how much is the area change if the radius doubles? 4A. Okay, so this is the L prime and A prime. And so if we look at that relationship to R naught, which is rho L over A, we see here that we've got a 2 divided by 4, and so R1 is equal to R naught divided by 2. Because it's 2/4, and so in other words, we made the resistance by doubling the radius, we made the area 4 times bigger. We made the resistance 4 times smaller. But then we had twice as many obstacles to run through because we had twice the length. So you have double the length, but only the resistance of the wire is only 1/4 as much. And so that gives rise to a reduction in the resistance by a factor of 2. Are there any questions about that? Okay, so that would be an easy kind, not on the two-state quiz, but that would be almost guaranteed. You see something like that where I change the radius and the length, and then you just figure out what the new resistance would be, how that would relate to the old resistance. But what if the current density does vary as a function of R? Then we don't have this simple relationship anymore. We have to write it in terms of a derivative. So let's say that J, in this example, is 10 over R, as I have written here. And I'll pass this out. I didn't have time to make a copy of this for you, but I'll pass this out during lab this week for these notes. Okay, so I then, if we think of the current density as di dA, then di would be j dA. And I total then would be the integral of j dA. And so this is for a current that varies over the cross-sectional area of the wire. So in this case, the current is going to be bigger toward the middle of the wire and smaller toward the outside, 10 over R. And so if we plug that into this expression, then what's dA? Well, A, if this is a constant cross-sectional area, A, we can say that dA is equal to 2 pi R dr. So at some radius r, you've got a circumference, 2 pi r, times the thickness, which is dr. And so we've just plugged that into this expression. We'd integrate this from 0 to big R. So this would be 10 over R times 2 pi R dr. So the r's would cancel, and that would give us 20 pi times big R. Okay, so that'd be 20 times pi, and in this case, let's say that big R was 1 centimeter. And this would be 20 times 3.014 times 0.01 meters. And so that would give us a current then that would be equal to 0.628 amps. So that's what we do then to get the current if the current density changes as a function, in this case, of R over this region. So in this case, the R's would cancel, so you'd be integrating dr, and so that would just be R evaluated from 0 to big R. Any questions about that? Okay, now before I get to what would happen if you have a current over a changing area, what I'd like to do is introduce a puzzle that we could try to solve. This was first brought up by Richard Feynman, or at least that's where I first heard of it, in his lecture series on physics. And so the question is, we have, because of ultraviolet radiation coming in from the sun, what ends up happening is that this produces ions. And these positive ions tend to drift down toward the surface. So the electrons are knocked off, and so the positive ions then make their way down toward the surface. And so we have this net flow then of positive charge caused by UV radiation. And so that's observed, and we know that that's happening because the positive ions have an electron knocked off. And so they're naturally going to be a little smaller and easier to drift down toward the surface. But what's observed is that the Earth has a net negative charge, not a net positive charge. Not only that, but at the rate at which we calculate the positive ion flow to take place, it should cancel out the negative charge in about 45 minutes. And then you'd reach some equilibrium positive value. That the positive ion flow should cancel the negative charge that's observed. In less than an hour, about 45 minutes. But this doesn't happen, obviously. What we instead observe is, and this of course is on a perfectly flat surface, so we don't have to worry about disruptions in the curvature. we essentially have an infinite plane of charge because the Earth is locally flat. The net negative surface charge and the electric field near the surface, on the average, is somewhere around 100 volts per meter. So that's what's observed, and it doesn't cancel out in 45 minutes. So the question is, why? Anybody have any thoughts about that? Yeah.
My thought would be that all the electrons that are coming off of the ions, when the ions are produced, you have like all this negative charge still there. It didn't go anywhere, so it still has to come back down to the ground. It would like in the form of, I would guess, lightning.
Okay, lightning. Good. That's the subject of this special topic is lightning, and so that's the answer. Very good. Lightning. So what happens then to produce lightning can, when it finally reaches equilibrium, more than make up for the positive ion flow, which then moves toward the surface, but is more than compensated for by the negative charge flow from lightning strikes. So what's happening then when this occurs? Well, a number of things can happen. One of the problems with knowing exactly what happens is that you've got to fly through one of these clouds while it's producing lightning in order to take measurements. But by doing that, the plane itself becomes like a lightning rod. And so you can get the plane being struck as many as 1,000 times by lightning while it's moving through the cloud trying to take the information. That's very dangerous. And so we don't know as much about this as we'd like. But one thing that we think we have a pretty good idea about is that you have rising air. Now the rising air tends to come from the fact that a high pressure region will come in contact with a low pressure region. And then the high pressure region will be pushed up because it has lower density. And so the high pressure region rises and expands. This is called an adiabatic expansion. So if you take your warm breath and you blow on your hand, right next to your hand, feels warm. Time it gets out to here, it feels cool because the air has expanded that fast. And in the process of it expanding air cools. So the delta U for this is equal to P delta V, where this is the change in volume. And so as the gas expands, it cools because this is expanding. That means that we are essentially going to a lower state of energy. And so normally what you try to do is pull in heat from the outside. But if we have a rapid expansion, then there's no time to absorb heat from the environment. So that means that the internal energy is a drop in temperature. It goes, hey, you mind if I borrow some heat so that I can expand? It goes, sure. Well, I kind of wanted to be the temperature I was, but I'll give you some of my internal kinetic energy so that you can expand. So it drops the temperature. Once the temperature drops, then the water freezes. And so you've got these rising ice pellets, and then when you get to a high enough altitude, they start to collect together into graupel. And so you've got this dropping which are these bigger ice chunks. that start to fall down. And so they rub against each other. This is what we think happens. And as they collide with each other, going up and going down, what this tends to do is create a charge separation between the bottom of the cloud and the top of the cloud. So this is caused by the ice crystals, we think, rubbing against each other, and the graupel then tends to grab more electrons, and then that's deposited to the bottom of the cloud because the graupel is more dense, so it tends to sink, and the ice crystals are being pushed upward by the air. But the weight eventually gets to the point where the gravity forces dominate, and so that's how the negative charge is deposited to the bottom of the ground, to the cloud. Then eventually, what that results in then is a pooling of electrons, and they start moving very slowly at first. Okay, and so this is not a lightning bolt yet, but this is the electrons trying to work their way down to the ground. Now the ground already has a negative charge from other lightning strikes, but nearby to one of these negative charges, we get induction. So induction then, even though the net charge on the Earth is negative, those negatives are pushed away in the vicinity of the cloud and creates a positive induced surface charge. And so this is called a stepped leader. And so this is just electrons moving down from the cloud, but not moving at the speed of a lightning bolt, maybe only moving at a few centimeters per second. And so they move slowly at first until it gets close to the ground. And then that starts inducing an even, when it gets within a few hundred meters of the ground, that pushes away even more electrons down here. And it causes these plasma filaments to start to reach up toward the stepped leader. Okay, and so these things are called streamers. So the stepped leader then is moving its way down. That creates these weakly luminous plasma filaments. Plasma is a hot ionized gas. And then you have other streamers coming up. And the first one to connect is the one that closes the circuit. So if you're standing down here on the ground, and your hair starts to stand straight out, it's because you are nearby, probably, there are other variations on this, but probably what's happening is that one of these plasma filaments is reaching up from your body to try to connect with the stepped leader. So the stepped leader is coming down like this, but then it's being competed with by others. So maybe the top of a tree is sending its plasma filament up. And so the first one that connects closes the switch and delivers something like 10,000 amperes worth of current to the ground. Maybe enough to power Los Angeles for a day. It all comes down in one of these big lightning bolts. And so if your hair starts standing straight out, then that's an early warning signal that you may be the path that that lightning bolt decides to choose in order to deliver those negative electrons to the ground. So what do? Well, do you think you run under a tree?
Probably not.
No, because the tree has its own plasma filaments that are reaching up and that they're taller than you are, and so that one may connect first, right? That one may be closer to connecting with the stepped leader, but aren't you protected? No, because the electrons then will flow down through the ground and follow this unfavorable path through your body. And you're right nearby to this thing, and so you're going to feel that flow of electrons going up through your body. So what's a better idea? Well, if you can get indoors, that would be the best. Sometimes if you can get in a car, that's good, because it's what's called a Faraday cage, and it can divert the electricity around the shell of the car and into the ground. But if you're stuck out in the open, the best thing to do is to crouch down and stay low, but not so low that you fall over, because the second that you put your hand down, that's the moment that the lightning bolt will strike by Murphy's Law. And that'll come up through your heart and then out, and then that is going to be way, I mean, this isn't a great path for the electrons to flow, but it's not as bad as going through your heart. So you want to stay low, but not so low that you lose your balance. And you don't want to lay down on the ground either, because if you lay down on the ground, then the voltage difference can increase. And this is something that I'll calculate for you in a little while, how much the voltage will increase if you have a greater distance this way. And that's what will happen if you lay down flat. So you want to get low so that maybe one of the other plasma filaments, the streamers, will connect with the step leader. But you don't want to get so low that if the lightning strikes, it has that longer distance. It's electric field over distance is voltage difference. So you can have a significantly greater voltage difference if your feet are farther apart. So the closer your feet can be together, the better, and the lower you can be, the better. Any questions so far? Okay, so with that in mind, I've got a very informative video. This also looks at the possibility that lightning can go, in some situations, in the opposite direction. Normally, this is the situation. Usually, when lightning strikes the ground, it goes from cloud to ground. But there are other situations where you can have the surface more negatively charged and more positively charged up, for example, in the higher atmosphere. And so this can give rise to really powerful lightning bolts that can last like 5 seconds. So these ones that go from the ground up are much more formidable, but they're less common. You know, maybe 10% of them go from a positive ground from a negative ground up to a positive region high up in the cloud.
Laws and whatnot exacerbate misunderstandings about lightning. Over the decades, I've seen lightning do some freaky stuff. In this video, we're going to explore and explain the weird world of lightning. Thunderstorms have the ability to separate pools of positive and negative charges in and around them, thus creating powerful electric fields. Lightning is born between two oppositely charged regions, as a network of electrically conductive channels called leaders materialize and begin to tunnel a path through the poor conductive air in between. Think of leaders as a sort of jumper cable. The leaders branch out in two directions, each with opposite polarities, toward both regions in an attempt to neutralize the charge separation. Most lightning flashes occur within the storm and are called cloud flashes, or intercloud lightning. But when one end of the bidirectional leader network connects to the ground or object on the ground, we call it a ground flash, or cloud-to-ground lightning, CG for short. In the most common CGs, a negatively charged step leader approaches the ground. The electric field between the step leader and the ground strengthens to the point that an oppositely charged positive leader begins reaching up, bridging the gap between the two. More than one upward leader may initiate an attempt to connect with the downward leader. However, the first to reach a downward propagating step leader will suddenly complete a channel path through the resisting air for the flow of powerful electrical current between the Earth and cloud. Electrons then rapidly accelerate down the channel, causing extreme heating and the brightest flash of the event. This is the return stroke. In rare photographs, you can see failed upward connecting leaders that didn't reach the downward leader first, and thus terminated into the air. The leader's return stroke and all the complex components of a lightning event is simply called a flash. The air around lightning becomes so hot that it explodes as a supersonic shock wave that transitions to an acoustic wave within a few meters. This rapid expansion of air molecules creates sound waves that radiate outward about 1 mile every 5 seconds. The sound we hear is thunder. In this clip, at 2,000 frames per second, you'll notice 2 distinct types of leaders with different behavior. You can see the positive end of a leader scouting a pathway through the air, but notice the flickering segments that follow. These leaders form on the decayed segments of highly branched positive leaders and are referred to as recoil leaders. Cloud-to-ground lightning strikes are characterized as positive or negative, depending on the net charge a bolt shifts to the ground. If a negative leader with a surplus of negatively charged electrons connects with the ground, negative charge, primarily in the form of free electrons, is shifted toward the ground, and the ground gains negative charge. And so we call this flash a negative CG. Inversely, if a positive leader with a deficit of electrons connects with the ground, an induced surplus of electrons in the ground travel up the channel, shifting negative charge away from the ground up into the storm. The ground gains a net positive charge, so we call this a positive CG. Sometimes you'll hear storm chasers and meteorologists identify negative CGs or positive CGs in the field. So how can they tell the difference, and why does it matter? For starters, if directly struck, one could kill you, and the other will likely kill you. It's difficult to be 100% sure eyeballing them, but many positive CGs and negative CGs have visibly different behavior that you can see. Often after a negative CG return stroke, multiple other return strokes follow, causing the main channel to flicker. This is called a multi-stroke CG flash. Check out this multi-stroke CG actually sailing in strong winds. The strobing effect is partly due to the orientation of the charged regions in the storm. Most negative CGs initiate between a mid-level negatively charged region and a smaller positive charge region near the base of the storm. But the return stroke of typical positive CGs rarely flicker. Many occur in a positive pool higher in the thunderstorm and the ground. Because of the greater distance the leaders have to blaze through the resisting air, the return stroke of these positive CGs is often much hotter, brighter, and longer in duration. The peak charge of positive CGs can be 10 times more powerful than a typical negative CG, and thus considerably more dangerous. These are generally the most powerful CGs, reaching temperatures up to 30,000 degrees Celsius. That's roughly 5 times hotter than the surface of our sun. Positive CGs only account for about 5 to 10% of all ground flashes worldwide, but in Tornado Alley, they are an atypically common sight. I tend to see them just downstream of strong storm updrafts. Many of these positive CGs have a strange, smooth, and fluid channel near the ground due to a lack of branching in strong positive leaders. We refer to this as smooth channel lightning. The visible flash is often just the channel without any branching leaders, and so it's sometimes referred to as branchless lightning. But be assured, there is leader branching. It's just hidden in the clouds aloft. Sometimes a bolt of lightning can leap miles away from the storm, jolting earthlings with surprise. We call this a bolt from the blue. Outdated paradigms suggested these clear air channels leaping out the back of storms were positive in polarity. But the latest research using lightning mapping and high-speed cameras have shown most of these startling zaps are indeed negative. If you capture a bolt from the blue and it has a lot of branching, chances are it was a negative CG instead of a positive.
Now that you know some different characteristics of positive and negative ground flashes, see if you can tell if these CGs are likely positive or negative. It's pretty easy to see these differences in slow motion. Now let's see if your eyes are quick enough to tell the difference in real time.
Sometimes storms grow upscale into massive complexes stretching across states. These systems have horizontally layered charge regions that serve as the conduit for lightning to travel over 100 kilometers. Check out these massive horizontal flashes. If these horizontally extensive flashes connect to the ground, they are almost always positive in polarity. They transfer huge amounts of charge and cause abrupt changes in the electric field, which can trigger another flash in a sort of domino effect. Upward lightning travels up from tall objects on the ground into the storm, and usually always have upward propagating positive leaders. Frequently, these upward leaders will produce spectacular flickering from recoil leaders developing on decaying positive branches. This is also called ground-to-cloud lightning. Almost all upward moving flashes are triggered by a nearby lightning flash, either when leader activity or a return stroke occurs close enough to the tall object, causing an abrupt change in the electric field.
So if someone asks you, does lightning strike up or down? The answer is both. If they ask you how lightning works, let's change the subject.
Not only can massive horizontal ground flashes trigger upward lightning, they can act as the parent flashes triggering red sprites high above the thunderstorm in the mesosphere. Now that we have a general understanding of how lightning works and how one lightning flash can trigger another, it'll be much more simple to understand red sprites.
Ooh, yeah!
Sprites! Yes! Beautiful!
Guys, I know there's a lot of health and economic.
Okay, so that I think is pretty informative, maybe a little more information than we need for getting to an exam. The main thing here that I wanted to emphasize is that main thing that I wanted to emphasize here is that the most common kinds of lightning strikes are what they were calling the negative CGs. And so this is from cloud to ground. Something like 90% of the lightning strikes that actually hit the Earth are negative pools of electrons with the weakly luminous plasma filament, the streamers reaching up to connect with the step leader. And you'll see that as a series of flashes. And so that's the way that you can tell the difference they were talking about before. Why do you get the flashes? Well, because one part of the stepped leader will empty out first. Then the next part will empty out. Then the next part will empty out. And so you'll see that as a flickering until finally up in the cloud, maybe the rest of the negative charge will empty out after that. And so when they say the lightning never strikes the same place twice, that is not only completely wrong, but lightning always strikes multiple times in the same location as different parts of the step leader dump their negative electrons into the ground. The other kind is caused by the fact that typically you tend to get more positive as you get to greater altitude. And so a concentration of positive charge up here can induce a negative surface charge near the ground. And so this is the positive CG, where the electrons go from ground to cloud. But oftentimes they can go up even higher in the atmosphere because you have to have equal amounts of positive and negative. So it's going to be complicated in general. You're going to have a lot of negative areas, a lot of positive areas. But more typically, the negative areas tend to be lower down, and the more positive regions tend to be higher up. And so in the upper atmosphere, then, you can get a really strong concentration of positive, so strong that it can create a lightning bolt that goes from the ground to the cloud that can last 5 seconds. And so those are the most intense and most damaging. Because there's more energy released. But they don't flicker. And so if they don't flicker, then you can identify them then by the fact that they're extra bright, extra long, but the ones that go from the cloud to the ground are the majority of them, and that they tend to flicker. But of course, it happens so fast, sometimes you can't tell whether it's flickering or not. That all being said, the vast majority of lightning goes from cloud to cloud. Only maybe, and this is an estimate, but maybe only a third or a quarter of the lightning goes from cloud to ground, because it's easier to equilibrate your charge over a shorter distance within the cloud than it is to go all the way to the ground. But of course, we're more interested in the ones that go to the ground. But you are likely to see way more lightning happening up in the clouds than you do ones that actually come down and strike the ground. In terms of human injuries, something like 80% of people that are struck by lightning amazingly survive. 80%. That's 60% of the survivors have permanent injuries. Which shouldn't be too surprising, because you've got this gigantic amount of electric current going through your body, and your body's basically a bunch of circuits. And so you're blowing up the circuits in your body. And there was a situation where up at the top of Mount Whitney, it's not there anymore, but there used to be a tin shack up there. And so when lightning would start to strike, people would run inside the tin shack. And that would happen very often at these high elevations because clouds when they try to go over a really high mountain, they expand and they cool. And so that's what creates the Sierra storms. And so you get a lightning bolt striking here and you think you're safe because it's a Faraday cage, but no. It's like hiding under a tree because the ground, the lightning can still travel through the ground like that and through, and if they're leaning up against something, that could be even worse. Then it could have an even more unfavorable path than just up one leg and down the other. But there were 6 people up there in that tin shack. This is one of the reasons why they rebuilt it as a more solid structure that has better insulation. But the 6 people that were in there, they were all electrocuted, and one of them died. So that can happen then, even if you think you're safe in terms of the lightning not striking you directly, it can get you along one of those side routes. It's been, in the United States, the statistics are that 20% of all lightning strikes happen while people are playing golf. And so it's not too surprising because people are addicted to golf. And so they see the lightning coming, they go, I can squeeze in a couple of extra holes before it really gets bad. And but professional golfers a lot of times have very interesting stories about how they were sitting under an umbrella and the lightning bolt hit the umbrella and then they got pretty badly shot. I was going up Mammoth Mountain during the summer. One summer, I was hiking up there and I ran into this lady and she had this big, huge brace on her knee and she was walking and it looked like lightning was going to strike at any moment. And so somehow she always finds herself in this situation. She said that she was about a block away from a cliff face and she had touched one of the rocks. And so it went through and it blew out one of the valves in her heart. So she had an artificial valve put in and she was walking around with this knee brace. And boy, maybe make it a little easier there, but I felt like maybe I should get away from her because she seems to be in the wrong place at the wrong time. But those are the kinds of things that can happen then from lightning. Are there any questions about this before we do a numerical example? Yeah.
So for the tin shack, did the lightning strike it directly, or did it strike next to
it hit the tin shack, then it flowed down the side. So this is a lot like what would happen if you're in a car. But in a car, if you're sitting on the seat and you're not touching anything metal, then the lightning is likely to go out through the wheels into the ground. But in this kind of a situation, you're not really protected here on the ground. You just have the resistivity of the ground, which may not be that much. And so then the current can flow right through you. And so this is one of the reasons why lightning rods, when they are constructed, they have a ground wire that usually goes deep into the earth so that it doesn't just go to the surface, because then the electricity would just spread out all over the place and wipe everybody out. And so they usually put it deep down in the earth. And Ben Franklin is the one that first came up with the lightning rod idea, and the design really hasn't changed in 150 years. Okay, so let's say that we have a lightning strike, and here I'm going to make the resistivity of the ground 10 to the 4. Okay, and so that is definitely not a normal conductor, but with a little bit of water going through it, we could call that a modest insulator value for the resistivity in the ground. And so certainly we're kind of making an assumption here. If the lightning strikes the ground and it moves out uniformly in all directions, that the resistivity of the ground will be the same all the way through. And it may not be, because the surface ground may be wetter than what happens down below. So we're making some idealized assumptions here. But let's assume that we see a lightning bolt strike and we start running away. Okay, so here we are. Oh my gosh, I've got to get out of here. And really worried and running in that direction. Let's say this direction, this is 40 meters away, and your front foot is 41 meters away. With the resistivity of the ground being 10 to the 4 ohm meters. Okay? Let's figure out what the voltage difference is across your feet here as you're running away if we have a bolt that strikes let's say that that bolt delivers 10,000 amperes worth of current. Okay, so I here is 10,000 amps, A is 40 meters, B is 41 meters, and the resistivity is 10 to the 4 ohm meters. Okay, so how do we do that? Well, we go back to our basic relationship between voltage and electric field. So you go, well, we don't really know either one, do we? Well, we're given the current. And so we know then that the current is going to hit here, but then it's going to spread out through what we could consider here to be a spherical resistor. Okay, and so it's going to go out in all directions, but as it expands out, the current density is going to change because the area through which the current is moving is getting larger, as would be the case with a hemisphere, assuming that the drift velocity is the same in all directions. Then that's what we would have. So we could write then that the voltage is equal to the integral of E dot dr. And then we can use our basic relationship that defines electric field in terms of current density. So we can think of that then as being rho times J. That our resistivity rho is times the current I. Now that current I is given here. That current is 10,000 amperes. So 10,000 coulombs per second is being delivered into the ground at this location. It starts spreading out, not through a whole sphere, but through a hemisphere, because it can't go this way. The air isn't insulated, so it has to go through the ground, which has a smaller value for the resistivity. So the area then is going to be 2 pi r squared. Okay, so that's the surface area of the hemisphere. Remember, 4 pi r squared is the surface area of an entire sphere, but this is going out just through the hemisphere. And so the area then here is going to be 2 pi r squared. So we can plug that in here, and that'll give us the integral of rho I over 2 pi r squared times dr. Okay, so that integrates out to rho I over 2 pi, and then that gives us, well, it's minus the integral here, so the negatives cancel. When we have the integral of 1 over r squared, we get 1 over r. This is rho I. So these are all constants because the current is coming from the lightning bolt. That's striking at one spot. And so that's a constant value in this integral. But the way it spreads out is not constant. And so that's where we get our dr over r squared. And we'll integrate that from r1 equals a to r2 equals b. So in other words, we're going from here to there. We're integrating from here to there this expanding electric field. And so that gives us, because this was negative to begin with, then this is minus 1 over r. And so we get rho I over 2 pi times, and we have 1 over b minus 1 over a. So if we plug in the values of the resistivity 10 to the 4, the current 10,000 over 2 pi, we get a difference in voltage of 9,700 volts. Which, although sounds like a lot, if it just goes up through your legs and then back out the other side, you might be okay. Because we didn't say how long this lasts for. You know, at the moment that you land, you're going to get a certain amount of current delivered. The total amount of charge would be over the amount of time that the lightning bolt strikes. So we're not looking at the total amount of charge that you would feel, but we'd be looking at the voltage difference at that moment. So it'd be about 10,000 volts that would go through. And that's when you're, well, this is like, you think you're pretty far away, right? This is like, what, 120 feet or so, more than that even. And then one big step, 123 feet or something like that. But that's still enough to electrocute you at that distance away. And so if you were much closer, then these differences would, this would give rise to a much larger value here, and you could be up near 100,000 volts, or even more, 500,000 volts. And then in terms of the current that would flow through your body, then we'd have to think, well, what's the resistance of my body along that path? So let's say you had a resistance of your body of 100,000 ohms, then this would be about 1/10 of an amp would go through your legs. A 1/2 amp is enough to kill you, but that would be enough to shock you, but maybe not kill you. And so that perhaps is one of the reasons why something like 80% of people survive, but they get kind of messed up on the average. Any questions about that example? Yeah.
What would happen if you only had one of your feet on the ground?
Well then, all you'd have to worry about is the difference in the distance between one side of your foot and the other. So then this would be like 40 meters, and this would be 40.3 meters, and then you could conceivably have a current flow like that. But this is the reason why you don't want to lie down on the ground. Because then, instead of this being 1 meter, it's 3 meters, and then you have a less favorable path. Another thing to keep in mind is these are equipotential lines. And so this is the lightning strike here, and here, between there and there, this might be, I don't know, I'm going to make something up. Let's make this 100,000, and like make this 109,700. This is between 40 and 41. So the delta V here, I don't know exactly what the voltage is, but we know the difference is 9,700 here. So these are equipotential lines. This would be an equipotential line for 109,700. This would be an equipotential line for 100,000. So instead of running away like a coward, you stand up to it. Go, okay, I'm just going to take you on, and you face it. Then you're on the equipotential line and no shock. Okay, so this is an example then of being afraid of something causing more damage than just facing it. But the problem, of course, is that you're not going to know where the lightning bolt's going to strike. It's going to be too late to turn your body around once it's hit. But if you were on an equipotential line, then the delta V would be 0, because then it would be 1 over 41 minus 1 over 41, which would be 0.
Is this why, like, for those shows that try and like show you emergencies, stuff like that, like if a power line came down on your car, and from what I was told, you like break the window, but you jump out with both your feet together, and then you would try and I guess like scooch away from where the lightning is depositing into the ground?
Well, you're trying to keep your feet from being any distance apart.
Any longer distance, yeah.
Right. And so that would be the same idea as this, yeah.
Gotcha.
Any other questions? Okay, so next, what I'd like to do is look real quickly at how we might calculate the resistance for one of these spherical resistors. Okay, so once we realize that, yeah, this actually is something that has practical value, you can think of this as being like a spherical resistor. As the charge moves away, then can we look at a more idealized case and figure out what the resistance would be for a spherical resistor? And we know that for a long straight wire, the resistance is rho L over A. So, but what if the area were to change? Maybe we have a tapered resistor like this. So we have two different areas. And so the current density would definitely change, but the resistance that is associated with that would change too. So in this case, we could say dr is equal to rho dl over A. Where dl is the distance that you move in the direction of current flow, that over a varying area. Okay. And so we'll look at this example in a second. That's the one I have on the next page. But let's do this first for a spherical resistor.